Welcome to our mini lecture on equivalence relations and quotient sets. An equivalence relation is a mean to express that two objects in a set are essentially the same from a certain perspective. Formally, an equivalence relation on a set E is a binary relation on E, which is reflexive, every element of E is equivalent to itself, transitive, for all x, y, and z in E, if x is equivalent to y and y is equivalent to z, then x is equivalent to z, and symmetric, for any x and y in E, if x is equivalent to y, then y is equivalent to x. The simplest example of an equivalence relation is equality between elements on a given set, but it is also the very notion that an equivalence relation is designed to generalize. Another fundamental example is given by functions. So if you have a set E and some function from E to some other set, I'm going to say that x and y are equivalent if and only if f of x equals f of y. It's indeed easy to check that this is an equivalence relation on E, and we will see soon that in fact all equivalence relations are actually given by an expression of this form. When you have an equivalence relation on a set, you can define a notion of equivalence class for an element. The equivalence class of an element x in a set E is simply the set of all element y equivalent to x. The main observation is that equivalence classes encode the equivalence relation completely in the following sense. If you have a set E endowed with an equivalence relation, and if I have two elements x and y in E, then x is equivalent to y if and only if the equivalence class of x equals to the equivalence class of y. Let's prove our theorem. First, let x and y be elements of E such that y is equivalent to x. By definition, that means that y is in the equivalence class of x. Now, if I take z in the equivalence class of y, we must have that z is equivalent to y. And by transitivity, since z is equivalent to y and y is equivalent to x, we conclude that z is equivalent to x. So z is in fact an element of the equivalence class of x. Hence, we have shown that the equivalence class of y is a subset of the equivalence class of x. But now, the relation of equivalence is symmetric. Therefore, we also have that x is equivalent to y, and by applying the same proof we have just done, we see that the equivalence class of x would be a subset of the equivalence class of y. So indeed, those two equivalence classes are equal. So equivalence classes of equivalent elements are equal. Conversely, let x and y be elements of E whose equivalence classes are equal. First, because the equivalence relation is reflexive, x belongs to its own equivalence class. But then that means that x belongs to the equivalence class of y, since it's equal to the equivalence class of x. And therefore we conclude by definition that x is indeed equivalent to y. This concludes our proof that we have indeed transformed an equivalence relation on the set E into an equality between equivalence classes. Since equivalence classes encode the equivalence relation, it is natural to introduce the notion of a quotient set. So if E is a set with an equivalence relation, the quotient of E by this relation is a set of the equivalence classes of all the elements of E. Note that an equivalence class is a subset of E, so the quotient set is technically a subset of the power set of E. Now we have a natural map which takes an element of the set E and maps to it its equivalence class in the quotient, and of course it's a surjection by construction. It's called the canonical surjection for the equivalence relation. So if we have an equivalence relation on a set, then what we have seen in the previous theorem is that equivalence of two elements in the set becomes equality of the equivalence classes in the quotient. So in some sense, we group elements in such a way that we make a new set where what was equivalent before is now truly equal. That's essentially the whole point of being a quotient set, of the construction of these quotient sets. So now I'm going to take a slightly different perspective. Instead of taking about binary relations on a set, I'm going to talk about partitions and see that partitions and equivalence relations are essentially two sides of the same coin. So a partition is a mean to group elements of a set in distinct classes. You kind of partition your set. And a little bit more formally, it is a cover of the set by disjoint and non-empty subset of E. So formally, this reads like this. A partition of a set E is a subset P of the power set of E. The elements of P are subset of E, such that, first of all, if you take any element of your partition, it is not empty. It's not an empty subset. Second of all of E can be written as the union of your partition. So if you take everything that is in your partition P and you take their union, you get all of E. And third, if you take any two elements of your partition, C and D, well, if C is not equal to D, then actually C is disjoint from D. So distinct implies disjoint among the elements of P. That's the definition of a partition. In particular, if I have a set E endowed with an equivalence relation, then the quotient set of E by this equivalence relation is a partition of E. Remember, the elements of the quotient set of E by relation are the equivalence classes for this relation, so they are subsets of E, and this theorem tells me that these subsets taken together form a partition of E. Let's prove our theorem. First of all, if X is an element of E, then X must belong to its own equivalence class, since an equivalence relation is reflexive. So in particular, no equivalence class can be empty, and moreover, E is indeed the union of the elements of the quotient set, namely it's a union of all the equivalence classes. Second of all, I'm going to prove that if two equivalence classes are not disjoint, then they must be equal. So let X and Y be element of E, such that their equivalence classes are not disjoint, and let's pick Z in the intersection of those two equivalence classes. Since Z is in the equivalence classes of X, Z is equivalent to X, and so by symmetry, X is equivalent to Z. And since Z is in the equivalence class of Y, Z is equivalent to Y. So we have X equivalent to Z, and then Z equivalent to Y. So by transitivity, we have X is equivalent to Y. And we have just proven that that means that the equivalence class of X equal the equivalence class of Y. So indeed, equivalence classes are either equal or they're disjoint. And this proves that the quotient set is indeed a partition. Now, on the other hand, it turns out that we can flip this picture. Partitions also induce equivalence relations. So if I have a partition of a set E, I can define an equivalence relation as follows. I say that two elements X and Y in E are equivalent if they both belong to the same elements of my partition. Well, I would claim that this indeed is an equivalence relation on E, and not only that, but the quotient space is exactly given by the partition I started with. If you put this theorem with the previous theorem, there is therefore a complete duality. You start from a partition, you can make an equivalence relation, and the quotient space gives you back your partition. If you start from an equivalence relation, your quotient set is a partition, and of course if you feed it into this theorem, you read that the partition in question, you define this new equivalence relation written in the theorem, and you get back the original equivalence relation. So it's a completely symmetric picture between those two notions. The proof of our theorems goes as follows. First, I'm going to show that the relation R is reflexive. So let X be an element of my set E. Now, by definition, E is a union of all the elements of the partition P. So there must be an element of that partition, let's call it C, such that X belongs to C. But by definition of R, it means that X is related to X, and therefore I have that R is reflexive. And symmetry is completely trivial if you look at the definition here, right? If two elements belong to a set, it doesn't matter in which order I list them. So I'm left with proving transitivity. So I'm going to take three elements in my set E, called X, Y, and Z. with the assumption that x is related to y and y is related to z. So what does that mean? Well, x related to 1 means that there exists an element C of my partition so that x and y both belong to C. And y related to z, what does that mean? It means there exists another element, let's call it D, in P such that y and z all belong to D. But then what we immediately note is that y is the intersection of C and D. It's common to both. And since P is assumed to be a partition, that means that C must be actually equal to D. And suddenly, x and z both live in the same set C, say, in my partition, which by definition means that x is related to z. So as a reflexive, symmetric, and transitive relation, R is indeed an equivalence relation on E. It is now natural to ask what the quotient set should be. So we start a little bit the same. We fix an element x in my space E, okay, and I'd like to know what the equivalence class of this x is, right, in terms of the partition P. First of all, again, like before, since E is covered by the partition, the subset of the partitions put together makes E, there must be an element C of the partition such that x belongs to C. And moreover, because P is a partition, this set is unique. There is no choice in what C that could possibly be. There can only be one. There is one, but there is only one. And the reason there is only one is because if x was common to two elements of my partition, those two elements would have, in fact, to be the same by definition of a partition. So we have this unique C containing x among all the elements of P. And now suppose that we have an element in the equivalence class of x. So that means an element y that's equivalent to x. Well then, by definition of what this relation R is, that means y belongs to C as well. And if y belongs to C, again, by definition, it means that y is equivalent to x. All right? The reason why we have these two things is very easy. I mean, since x can belong to only one set, if x and y must belong to the same set, that has to be C. And conversely, if ever y belongs to the set C2 in which we already know x belong, that's the definition of R, that they are x and y are equivalent. So very, very simple, but that tells me that the equivalence class of x is exactly given by this element C of the partition. So with this, we see that the equivalence class of any point in my space is given by one of the elements of P. Now, if you take an element of P, it contains at least one point because it's not empty, and therefore it's the equivalence class of that point. And therefore, we have shown that the quotient set is indeed equal to the partition that I started with. And that concludes our theorem, and also this equivalence, so to speak, between equivalence relation and partitions. Let's conclude our lecture with a factorization theorem. Let R be an equivalence relation on a set E, and let pi be the canonical surjection from E to the quotient set E quotient by R. Let f be a function from E to a set H. The following two assertions are equivalent. Assertion 1. If x and y are elements of E that are equivalent, then f of x equals f of y. Assertion 2. There exists a function g from the quotient set E quotient by R to the set H such that f is equal to g composed with pi. So we indeed factor f for the composition. The proof is pretty much straightforward. So first, let's assume that f is constant on the equivalence classes for my relation R. Let A be an element of the quotient. Since pi is surjective, there exists a point x in the set E such that x is equal to pi of x. What I would like to do is set g of a equals f of x. And that works because if I choose a equals pi of x and someone else choose a equals pi of y, different x and y in E, that gives you the same element in the quotient space, then by definition we know that x and y are equivalent, and we know that f of x therefore is equal to f of y. So whichever so-called representative or element of E you choose, which maps to A by the canonical surjection, or in other words, any element you take that is in the equivalence class A, then the function is constant there. There is no ambiguity, and we can define g of A to be whatever that constant value on that equivalence class is. On the other hand, if f is factored at the form g composed with pi for some function g from the quotient space, Well, again, then if you take any 2 point x and y in E that are equivalent, then we've proved early on that it means their image by the canonical surjection are equal. In other words, their equivalence classes are equal. And so if you just calculate f of x is g of pi of x, but pi of x is pi of y, so g of pi of x equals to g of pi of y, which by definition is f of y. So we see that f is constant on the equivalence classes. Couple of comments. First of all, we see that we can actually use the theorem to fabricate bijections out of that regular functions. So if you have, a function from e to h, like written here in the theorem, with two sets e and h, what you could do is define the equivalence relation that we saw at the very beginning of this lecture, where 2 points in E are equivalent if and only if f of x equals f of y. So if you do that, then you have, I claim, an injection, G, from the quotient space to H, such that indeed f equals G composed with the canonical surjection for this equivalence relation. So we can rewrite f as, well, f is not necessarily injective, but we can factor it through an injection. Okay, so that's one comment. And the other comment is we sort of come full circle a little bit, because you see now that, of course, if you give me an equivalence relation, then there is a canonical surjection going from a set to the quotient set. And we've discussed that the equivalence relation, in that case, can be rephrased simply by saying that the image by this canonical surjection of 2 points are the same. That's what it means for 2 points to be equivalent. So we've seen that this example that I started with the lecture, where we had equivalence relation defined by equality of the images by some given function of 2 points in the set, is in fact universal. Every equivalence relation can be expressed this way, and this is a good point to conclude this mini lecture.